Believe it or not, but the clock will appear different in different systems depending on the relative velocity. And this is called time dilation, and it's one part, a very important part of the theory of relativity. Let us have two systems. One called K, which is in rest, and then we put a clock in the other system and let this system, which we call K prime, be moving with the velocity of u in this direction. So here I have a clock which will be we will be sending away with the velocity. And the clock consists of an emitter and a reflector here. And the light pulse will be emitted and reflected back. And the distance between these two is equal to L0. And an important consequence of that the velocity of light is different it's the same in all inertial systems, in all systems at all, is that the clock will appear to go in different speed. So let us define the time interval in this system, measured in this system, as the time it takes to go to the mirror and reflect it back. So we have a light pulse here, and it takes the time t1 prime, and this is equal to L0 divided by the velocity of light, and then we have t2 prime. It's the time it takes for the light to go back, and this is L divided by 0. It's the same. But it's quite different in this system where the clock is moving with this velocity. We have the same speed of light, but the path will look different in this system because the clock is moving. It can be shown that this distance from the emitter to the reflector, as seen in this system, will be the same as the length seen in this system. So this will also be L0. This distance for the light ray in this system will be equal to the velocity of light times the time it takes to go from the emitter to the mirror, and this is Ct2. And this distance will then be u times t1, and this will be u times t2. So t1, we get t1 from the Pythagoras theorem. C t1 squared, the hypotenuse, is equal to the Cartesian L0 squared plus y t1 squared. And C t2 squared is equal to L0 squared plus u t2 squared. And from this we get t1 equal to the square root of L0 squared divided by C squared minus u squared, and t2 is equal to the square root of L0 squared times C squared minus u squared. And now we can compare this time interval t1 plus t2 prime in this system with the time interval in this system where the clock is moving with the velocity of u, t1 plus t2. And we get t1 plus t2 divided by t1 prime plus t2 prime will then be equal to 2 of this back terms c squared minus u squared divided by 2 L naught divided by c. And this can be reduced to 1 square root of 1 over u squared divided by c squared. And here we see that this time interval, which we can call t, is equal to the time interval in the system where the clock is in rest, t prime, divided by 1 minus y u squared divided by c squared. So, the time interval in this system is t prime, and the time interval for the light defined in time interval in this system will be longer by this factor, which we call the gamma factor. This is 1 over this factor is the gamma factor. So this is the time dilation. The clock moving will appear to go slower than the clock in rest. Clock in rest and the clock is moving by this factor.